Hello guys, welcome back to my channel. Mason African Motives are still working on engineering science and force. So in this platform we have got a paper that we are going to focus on statics, which is April 2019. All right, so we have the question, the first part of the question, and also the other part here. So this is the other part that we have got of the question to make it actually 15 marks here. So let us just quickly rush through the question and see what we have got. The first part, we are given that there is a beam of which is having a mass of 20 kgs over a length of 10 meters and is supported by A and B. Okay, so that is the information. So I'm just going to take this because the first part is just to draw a neat detailed sketch. We are given the supports here, A and B. So the first thing that I want you to understand here is that we have got the mass over a certain length, which is 10 meters in this case. So it means that this is going to be distributed load that we have got for the rest or for the whole of the 10 meters. So what we need is to know the force that we are going to have per meter. So it's going to be force per meter, that is per the given length that we are going to have. So this is actually a per meter, which is from your length. And remember that your force, guys, that's mg. So we are going to have, in this case, the mass that we have got, which is 20 kgs by 9,8, everything over the given length per meter. Now for us to have per meter, so it's 10 meters. So the moment we divide this, remember this is your force here, which is measured in Newton. So let us just write the units here. All right, so if we divide this, we are going to obtain something like okay, the first part is 196 Newton over 10, which is going to give us 19,6, that is meter here. So you've got Newton per meter. So this is distributed over 10 meters. Okay, so our diagram is going to look like this, guys. Already take note, you're given the reactions of the supports there, so it's going to be easier because it's just indicating the points already. Everything is given. So let's say that is what we have got, sorry, let's take down the measurements and everything. So the first part that we have got is we have said we have got a distributed of 20 kgs, which gave us 19,6 for the whole of what? For the whole of the 10 meters that is supported. So which means for the supports that we have that are A and B, which are 3 meters apart. Okay, let's see that we have got, it's true that B is 3 meters, but these supports that we have got, they are within this 10 meters. So it means that everything is affected by what? By the distributed. So let's just say this is what we have got here. I don't know if it is going to be clear. Let's just put it this way, that to say this is it's distributed throughout. All right, throughout until the last part that we have got here, and it's actually 19,6. We said 19,6 Newton per meter, remember. So let's just say 19,6 Newton per meter. All right, so let's just put this way again. Let's take, so you can even write mass, it's fine. The support that we have B is the one that we are given, that B is 3 meters from the right end. Okay, so 3 meters from the right end, which means this is your right end. So 3 meters, let's just say it this way. There is a support there that we have got at what? At B, which is 3 meters from the right end. All right, so this is from the right end, maybe somewhere here. 3 meters from the right end. Let's say this is somewhere here. So this is our right end, and in between here we have got what? That is where we have got our 3 meters. So this is the part B. Take note, guys. This is what? This is B, which is 3 meters from the right end. So this is your right end, actually. This is where we've got our right end here. But we are saying that these two, they are 7 meters apart. A and what? A and B, they are 7 meters apart. So it means if here we have got our B, to the point where A is on the other side. Sorry, we are going to have what? We are going to have 7 meters. So definitely, if we are to see that if here we've got 7 meters apart and we've got 3 meters here, that is the whole of the beam. So your A is going to be at the left end. That is where your A is going to be located, because 3 plus 7 is totally the whole beam as it is. So your A is going to be at this point, at the end here. That is where we are going to have our A. So this one is a support. Okay, so that's what you're going to have at the end there. So that is what you're going to have, guys. And we said we've got 7 meters in between here, between A and what? Between A and B, that's 7 meters. So as you can see, 7 plus 3, you already have what? 10 meters. So this is your support A here. And the other thing that we are given, guys, are the support, the reactions of these supports. So let's just write them aside so that we don't face challenges later on. So this is A, which is 43.143. So this is 43.143 Newton here. And your B, which is 182,857. So this is 857 Newton, this one. All right. So this is what we have. And what else do we have? There is also a concentrated load, which is 30 Newton on this right end of the beam. So there is a concentrated load, which is one at the far end, the right end. So which means we are going to represent it going downwards. So it is going to be like this. All right, that is a concentrated load here. So that's what you're going to have. And this is a 30 Newton. Remember, you are given this is a 30 Newton like that. All right, so this is how it is going to look like. Do we have anything that we actually left here? Nothing. So we can even put this point, because we've got A, B. Let's just put this way as our C here at the end. And that's it. So like I said, guys, you can even write this as your mass, just to say your mass here is 20 kgs. That is, if you want, or 19.6 Newton per meter. But I think that is clear, guys. Okay. Anyways, let us see what we have got here on this part. The other part is to draw a neat detailed shear force diagram. Okay, so you know that for us to have the shear force diagram, right, we are going to, this is our first part. It is 5.11. So what I'm going to do is to use this diagram like to work out the second question. So but on your first part, this is like this, you are done. Okay, but I'm going to do some adjustments, because now I want to attempt this question, which is on drawing what? Your shear force diagram. So for us to have our shear force diagram, this is what is going to happen, guys. I'm focusing on our diagram here. Take note, we've got distributed load. So we want to know what is in between A and B. We want to know what is going to be like the concentrated. So this part now, I'm doing this adjustment so that I can attempt the second question. But just this, you are supposed to just leave it on like this on your first part. But here, because I want to attempt this question, that is why I'm doing these adjustments here, guys. So sorry for that. So what you're going to have in this case, even you can just leave it like that. But what you just need to know is that in between here, you've got 19.6. That is the force that we have, 19.6 times the distance, which is what? Which is 7 meters that you're going to have. And it will be separated in between what? In between 3.5 and also here 3.5, because this 7 you divide. So you just multiply these two and obtain a certain force, which is the same thing that you're going to do here. So these are the adjustments that you just need to know so that they help you to attempt the question. So here you'll be having 19.6 times the distance, which is what? Which is 3 meters. And it will be divided now into 2. That is 3 divided by 2, which is 1.5 meters, and also 1.5 meters. So like I'm just saying, you must visualize something like this so that you can attempt the second question. So now let us try to draw the shear force diagram. So in this case, remember the first part we already have the support is given. So whenever you're given a support, it's a positive, is going upwards. So we are going to have let's have our horizontal line first, where we are going to have it is going to be like this. Let's just put it somewhere here. Oh, sorry for that. All right, so we say this one is going up, all right, because it's a support. Always a support is going to be represented upwards. So let's just say at this point, that is where we are going to have it. And also the other thing that we have got here is supposed to be corresponding, actually, like we are supposed to have something like this, all right, corresponding actually to this point, to say this point is going up and this point is going to correspond here, this point is going to correspond. That is what you're supposed to have in exact form. But now, because of the space and everything, but this is the exact thing that you're supposed to have. So I don't know if it is going to be clear on this part, but let's just see guys, if it is going to be fine here, because I hope it wasn't going to be fine. So let's just put it this way. Okay, so this one, you're having this part here. Guys, this is not going to be clear here. Let's just put it aside. All right, so we said we have got 43,143 Newton. So you just take it, but along these lines, like what I'm doing. Okay, so now what you need to know is what is going to happen at B. So here, as we can know, that there is going to be 19,6, which is affecting us here. So, but we have, if we are to multiply this by 7, we are going to have something like this from our calculator, which is 137.2 Newton. So make sure that you multiply properly there. So we are going to subtract before we reach the point B, that is in between here. We are going to subtract because this is going down and it's a distributed load that you have got in between A and B. And you remember, a distributed you have to represent with what? A diagonal line like that. So that means at this point here, you are going to subtract. You are now at this point, sorry, at 43.143 Newton. You subtract the distributed load now, which is now represented like a concentrated load, because you have what? Multiplied everything by what? By 7. So this is going to be 137.2. Okay, so if you subtract this, you're going to obtain something like minus 94. That's minus 94,057 Newton. So which means this is going to the negative side at minus 94. So from this point we must reach negative. Okay, so let's just say our negative is somewhere here. So we are going to join from this point to this point. Remember, this is a what? A distributed load. So it is going to be like this. All right, at this point, that is at minus 94,057 Newton. All right, at this point. Now we are at point B at this point. So we have covered from this point up to point B, that is these 7 meters. So we are now at point B, and we do not have any distance separated between these 2 points. It's just a directed point B. There's a support, and the support is a positive. So we are going to add this now to this value that we are now. Okay, so we are going to add 182, the value of what? Of B. So remember, you are at minus 9, so minus 94,057 plus the value that we have got at B there. Okay, so if we add that value, you are going to obtain 88,8 Newton, the value at B. So this is a positive that you're obtaining, and it's a support, and the support, when you present on your shear force diagram, is going to be vertically up. Okay, up to 88, and it's above this value here. It's actually above 43, so it's going to be somewhere here, somewhere there, something like this. All right. Oh, guys, okay, something, let's just leave it. That's something like that. So this is going to be 88,8 Newton, something like that. That is where we are at now. From what? From B. Now, if you are to cross-check, at this point B, are now part of the distributed load again, which is we are now going to subtract this 19.6 times 3, which is going to give us 58.8 Newton. Okay, so we're going to subtract the distributed load that is going downwards at this value that we have. And remember, always a distributed load is going to be like this. Okay, so let's subtract at this value that we are now at 88. So it's going to be 88.8 minus this value of the distributed load, which is 58.8, and this is going to give us something like 30 Newton. So 30, where is it located? It's below this because this is 43, so it's going to be located, just say let's just say somewhere here, yeah, somewhere there. Okay, so but joining from this point just below that line, so let us just join here. Is going to be like this. That is where you are now at 80. So take note how you take your values. So now at 30, what happened from this point at 30 there? Let's see what happened. Just at point C, because this is corresponding with C, just at point C, which is the last end at C. This is at point C, this is at point C. There is what? There is a concentrated load of 30 Newton, which is a negative again. So this one goes directly vertically down. So you just subtract 30 to where we are. We are at 30 now. So if we subtract 30, what is going to happen? We are going to remain at 0 now. So it is going to be vertically down straight. So that is what you're going to have now at 0 Newton. So as you can see, that is how your diagram is going to look like. So this is it, guys, from this that was 5.12, all right, which is your shear force diagram. So like I said, it is supposed to correspond these points and so forth. And take note about the point here where it crosses, or the distributed load when it is crossing the horizontal line there, which is a very, very important point, which is going to affect us when you are now dealing with bending moments. I think I referred to this from so many classes, so we're just going to see that if it is going to affect us in this platform. Okay, so that was it. And the other question was now to determine the bending moments at the principal points. What are the bending moments? So this is what is going to happen, guys. The points that we have, which is in this case we are going to, okay, let me take our points direct. So in this case I'm going to calculate all the bending moments that you're going to have. That is in this case, let's start. Already the points that we have got is A, B, okay, then we've got C, and also we referred to this point that we talked about here. Okay, so this point is actually in between. It's unknown where it is where it is actually between, like the exact point where it is, but what we know is that this point here is in between A and B. This is where it happened, because this is your A, your B, your A and your B at this point. So what we are going to have is an assumption of where we are going to locate the distance. So I'm going to explain this as our later part, but let's just say it is located somewhere at a point that is referred to as D, which has got a certain distance back to the point A, because it's in between A and B, but we don't know exactly where it is located. And let's just say the distance is X meters. So I shall talk about this. But talking of the bending moments at A, this is actually S0. As you can see, we are multiplying. There's no distance, it's force times distance. So these ones are direct. So let us just take them as they are direct. So this is 5.13. So we've got bending moments at A. So at A, we've got the force times distance. It's a positive, is going up. So 43 plus 43,143 times 0, which is going to give us 0 Newton meter. Okay, that is taken from what here, from the left. Okay, we move on to the bending moments at B. We've got the bending moments at B. So like I said, this one we are going to refer it later on. Let us use the exact point that we have. So at B, what we have at B, we have got A going to the point B with 7 meters. So it's going to be positive. Okay, so let's just start by A, which is 43,143 times 7. It's a positive, this one. All right, back to B. Then we have got, remember, our distributed load that we ended up multiplying and having what, 37,2 over a distance of 3.5 meters, because we divided this, it's now 3.5 meters from this 7. So it is going to be 137.2 times this distance of 3.5, and it's a negative, this one, it's going downwards, so it's going to be minus 137.2. So if you are having this 19.6, you're going to write it as 19.6 times 7 times 3.5, or times 7 over 2. Someone can write it as 7 squared over 2. It's one and the same thing. So it's going to be times the distance, which is 3.5, something like this. All right, so if we are to simplify, it's going to be a negative, this one, which is negative 178.199, okay, something like that, which is Newton meter. So this one is from the left, actually we're taking it from the left. Then we have got the bending moments at what? At C. This one is direct at C, and the moment at C, I'm just going to take direct at that point C, which is the force. It's a negative times the distance of 0 there, so it's going to be negative 30 times 0, which is going to give us a 0 there, Newton meter. So that is what you're going to have at what? At C. So these ones we are already given, and we already know like these points. Then what about this one that we talked about, which is going to actually give us the maximum bending moment in this case, which is where this part crosses or have an intersection with the horizontal line at this point, which is in between A and B. So for us to know the position or the bending moment there, we are going to assume this point to be, let's just say it's a D. So I'm going to have this diagram drawn from A to the point D, because it's in between A and B, so just assume this is our D. So we need the bending moment at D, so which means B is not important. So I'm going to draw from A to D, just a sketch to show you what am I trying to explain here. So this is what you have got at what? At your point A. So this is your point A, remember this is 43,143, okay, Newton here at A. So I'm saying that there is now a point that we have got where we need to find, which is at point D. So we've got D here, which is an additional point from all these points that we had. But remember, all that we have is throughout a distributed load, and now the distance, since we do not know it, we are just going to assume it to be X. So we are going to have a distance here of what? Of X meters. Here we are going to have X meters in between these 2 points. All right, but remember, this is distributed in between these points. We have got a distributed load here in between these 2 points. All right, so this is what we have of 19.6. I hope you are going to understand what is happening here. So this is what we have got of 19.6. Remember, that was 19.6 Newton per meter. All right, so it's divided over this X meter. So what you're going to do is that we know that we are going to have, definitely, if we have got the exact value, let's say we've got the exact value of the distance, we're going to multiply here 19.6 times the distance, so that we can know the force that is going downwards. That is now like a concentrated load. But in this case, we do not know this value, so we are just going to assume, so we are to be X. So that is why we are having X. So I'm just going to multiply the force now per meter times the distance, which is X. So it's going to be 19.6 times X, which is 19.6 X Newton. So this is what I'm having now, just like a concentrated load. Remember, guys, when you obtain this, even the distance, it is going to be affected. If it is the X, it is going to be X over 2, X over 2. So our major goal now is to find the value of X. Once we know this value of X, it's easier for us to have what? The bending moment at point D. So how are we going to find the value of X? Okay, using the concept of forces going up, that upward forces is equal to downward forces, we can actually work something up, because we've got A, which is going up, which is 43.143 Newton, which is equal to F down, which is now 19.6 X, because remember, force per meter times the distance. So it can be easier for us to find x by simply dividing by what? By 19,6 by 19,6 like this. So that's your x. So our x, which is the distance, is going to be 2,201 meters, something like that, which is in between here. So it means that we have got 2,201 meters here, which was our x. So that means even this force is going to be 19,6 times x, and our x is this. So 19,6 times 19,6 times 2,201. That will enable now to know the actual force that is there. And this will be something like 43,1396, something like that, Newton. So that is going to be like the force that is there. And even this distance, because you also need, because you're calculating the bending moments, so you also need like to know what's the distance here. So yes, you know that you're going to simply divide by 2, but if you divide by 2, what is that distance? It is going to be 1,1005, something like that, something like this, 1,1005, something like that. So using these values, you can actually have your bending moment now at D, which is going to be here. We said you've got the distance, the force is a positive actually here, 43.143 times the distance, which is what? 2.201. Okay, which is a positive to point D. Minus, now we have got 43 point, this is the force that you're going to take now, which is 43, 1396, so something like that. And the distance now is going to be what? This is a negative, that's why I subtract here. And the distance is from this point to D, which is this value 1,1, or you can just say this value divide by 2, but it's going to be 1,1005 like that. So this can actually give us the exact value, which is in this case is going to be 47,483, something like that, which is Newton meters. So these are the values now that you're going to use to draw the diagram now, the bending moment diagram. But guys, you see these steps there, these are the steps that are very, very important when you are working with. So you're supposed to like take these steps as they are, but some of these steps, if you now know how to do them, you can actually just visualize this, okay, like to see, okay, this is what I'm having, I'm supposed to divide like this. So you will not have like all this working, you just shorten up your working now. But for the meantime, that's what we have. So that was for just calculating the bending moments in this case. So let's see the other part now that we had. All right, which is to draw a detailed bending moment diagram. Okay, draw a detailed bending moment diagram. Okay, so our bending moment diagram, we are going to use our bending moments. Okay, so this is 5.14. So we are going to use the bending moments that we had. So this is our bending moment diagram. So using our bending moment, let's just say it's something like this, just like what we had, guys, on our shear force diagram. But this time you have to know what the type of presentation that we have got here. So this is what is happening. Our bending moments are like this, guys. We've got the first one, which is at A. This is one. We are now having another one, bending moment at D, remember, which gave us something like 47. It was 47,483 Newton, remember that. And this one is in between these points A and B. Remember, it's in between this bending moment. It's in between, because it was calculated between A and B. Remember, I calculated this saying it was in between A and B, because this was A, D going to what? To the point B. So starting with the bending moment at A, yes, we've got our bending moment here at A, which is at 0 here. This is 0 Newton. Okay, so this one is at 0 Newton meter here. This is at A. Then from A, we are supposed to reach point B, which is in the negative region, but it is going to pass through the point D. which is having this bending moment that we have. So it means from the point A to the point D to the point B that we are going to have in the negative, we are going to have a curve because it's a distributed load, remember? So it's going to be a curve. Remember how you represent a distributed load, it's going to be a curve, but it's going to pass through the point D, which is your maximum point, then down to the point B, which is in the negative region, because our B is in the negative, but this D is in between A and what? Is in between A and B. That is where your D is located. So if it is located in between, it means it has to pass through the point D. Let's say this is your point D now, which is 47,483 Newton meter. That is at point D. But here, going to the negative, we are passing now, we are going to the point D, which is the one that had to give us this negative. Okay, so this is your point B, which is negative 178,199. Okay, so this is what now you have at point what? At point B. Then at point C, we are now at 0. But throughout, it's a distributed load, remember? So you're going to represent your distributed load like this now. Back to what? Back to 0. So this is what you're going to have, a curve back to 0 like this. So you're now at 0 Newton meter, which is at point what? At point C, which is your last point. So that is how these points, they just look like, guys. Okay. So guys, you see that it's a lot. I don't know how you see the questions and so forth, but that's how they ask this. And let's just see the other part that we had, which is to determine the position of the center of gravity. Why? From the bottom upwards. Okay, so it's from the bottom going upwards, and we need to determine the center of gravity. Okay, so this is what you're going to have, guys. Remember, this is a cylinder and another cylinder and this one is on top of the other cylinder, so which means whatever that you're going to have, we are going to add the values. So remember, let's just have our shape, just have our diagram in an easier way. So I'm just going to put it this way. All right, let's hope it's going to be clear, guys. I don't know if it is going to be clear enough, but I just hope it is going to be. It is going to be, in Jesus' name. It must be. Is that so, guys? So let's just have here, and this is now shaking a lot because of these lines. Like it will be this. It will be trying to, sorry, it will be trying like to focus to see what's happening there. Why are these lines like this, and all those. So, but we'll just surprise this. So we've got our shape here. And let's just have our volume here. Let's just write this as V, and that is the center. I suppose here we need to have we are working with the center of gravity, remember? So we've got the center of gravity. All right, let's just write this as G. All right, and we are going to have our volume moment here. So let's just write volume moment here, so we can write it as VG. All right, and what about this column? Why am I? Which means they are just having an extra one. Okay, we can just utilize maybe for our calculations and so forth. Okay, so like I said, guys, the first shape, we have got a cylinder with this one. Let's just put it as A or B, or just 1 and 2, so you can write 1 and 2. So you're going to start with this one in the bottom, this one. Okay, so that's it, guys. That's our cylinder here. All right, so the volume, so remember that the volume of a cylinder is given by this formula, pi, that is area, base area times the height. So it's going to be pi d squared over 4 times the height. Okay, so that is pi times the diameter. You've given the diameter from this point to this point, which is 100 millimeters. So it's 100 millimeters squared over 4 times h, which is the height from this point to this point. That is your height, which is 80 meters. All right, from your mathematics, guys, remember. So this is going to be our volume, which is 66.2. Let me just write it down. 8318. Okay, comma 513. This is 513 or 531. 531. Sorry. So this is 531. Okay, comma 531, and this is like cubic millimeters because it's volume. Remember. So that's what we have there, and our center of gravity, remember, when you are working with a cylinder, y is equal to h over 2. Okay, that is the value of y. So in this case, our y is going to be h over 2. That is our height. That is 80 millimeters over 2, which is 40 millimeters. All right. Then the volume moment, that is your volume times the center of gravity. You just multiply these two. So let's just write VG1, which is going to be multiply these two numbers here. Sorry guys, that is 62 comma whatever that you have, this value times what? Times 40. Write this value as it is times 40, and you're going to obtain 25132.741 comma 24. So this is what you're going to have in this millimeter cubed, and millimeter is going to be millimeter to the exponent of 4. All right, something like that. So that is the first shape that we had, and the second part is just going to be like that, but this part is going to be affected now, the center of gravity. Okay, I'm just going to show you how it is going to be affected. All right, so this is the first part that we had. The second part, we have a cylinder again. That's a cylinder which is on top of another cylinder. So this is our cylinder 2. So our volume 2, remember the volume we just wrote it above there, pi d squared is not going to change because it's still a cylinder, guys. But what is the diameter now? The diameter of this shape, this is your diameter here, from this point to this point, which is 60 millimeters, and your 100 millimeter is your height. So that is pi times 60 squared over 4 times the height, which is 100 millimeters. So we shall have our volume in this case, which is going to be 282743,339. All right, that is a cubic millimeters. So that is your volume there. And now I want you to take note that it's true that our center of gravity is supposed to be y is equal to h over 2, but take note, we are above this 80 meters. We are going to add our h1 to this, okay, that we are having. So it's going to be h1 plus h over 2. That will be the total center of gravity. So which means your y is going to be h1 plus h over 2, which is your h2 now. So h1 in this case, which is 80 meters, so it's going to be 80 meters plus h2 over, which is 100 over 2. So it's going to be 100 over 2 like this. So that's going to be 50 here. So 50 plus 80, which is 130. So it's 130 millimeters. So that's it. So take note, guys, it's on top. So you add the height, the first height, to the center of gravity. Okay. But here it's just going to be normal, guys, as usual. Your volume times the center of gravity. So you're going to take this value, 28, whatever that you have, times 130 as it is, and you're going to obtain something like 367566. All right, something like that. That is 34,07. This is going to be 07, and this is the exponent of 4, just like this, guys. Cubic meters times cubic millimeters times millimeters, that is to the exponent of what? Of 4. So now this information here, how is it going to help us? This is what is going to happen. We need remember that your y in this case, the center of gravity is equal to the volume moment over the given volume. So it's actually the total of the volume moment, which is your Vg. So it's total Vg over the total volume. So you need to find the total Vg and the total volume. So you have to find the total volume here, which is you add, because this one is on top. You've got a cylinder that you have got, okay, then another cylinder which was placed on top again. So here you are going to add, okay. So you add these two, V1 and V2. So it is going to be V1 plus V2, okay. So if we add V1 and V2, we are going to obtain something like 91106 1,869 cubic millimeters. You do the same again on your volume moment. You add volume moment 1 plus volume moment 2. You're going to add, this is 2, sorry, this is 2. So you add this 1 and this 2 together. So if you add these values, that will be 61889,375, 531 if I'm not mistaken, but that is what you're going to have, guys. So this is your total volume moment, this is your total volume. So volumes, you add these volumes here. So this is going to give us our center of gravity here, which is y, which is written from this formula. So your y is going to be your total volume moment, which is your volume moment, this value here, which is a 61889,375,531 to the exponent of 4, okay, over the total volume. So this is summation for total volume, okay. So that's your total volume, which is 911 something like this 061,869, which is in cubic millimeters. So as you can see, guys, this is 3, this is 4, so you're going to left with millimeters here. So it's going to be 67,931 millimeters, so something like that. That is your center of gravity. So the center of gravity, guys, is the total of the volume moment over the total volume. So all you need, if you can know this table very well, it's going to be easier for you. The shape, the volume, the center of gravity, volume moment. Okay, when the shape is on top of the other like this, you add, okay, you add the volumes. So this is your cylinder 1, this is your cylinder 2. You find your volume. So the formula for volume, you must know volume of a cylinder. Then the center of gravity, these ones you must know, and to add the 2. Then after adding, you can now find your center of gravity, which is y, just like that. So that's what you had, guys, for Mason African Motives, working on engineering science and for till we meet again.